We are diving into the fascinating science behind Earth's most extreme weather phenomena, and as we reveal the hidden forces behind wildest weather events. Imagine a world where rain never touches the ground, and where tornadoes can set the sky on fire. Or why does one hemisphere bask in sunshine while the other shivers? Why do some regions crackle with lightning far more than others? Our universe, in its infinite complexity, has gifted us a home planet, Earth, that is a veritable theater of atmospheric drama. We'll journey from the planetary mechanics that dictate our seasons to the localized conditions that spawn terrifying twisters and ethereal phantom rains, and how even the seemingly empty spaces high above our heads play a crucial role in the daily weather report. So prepare to have your curiosity ignited. Stay tuned to uncover the mysteries that make our planet so dynamic and unpredictable. Let's dive in. Tell me why the Northern and Southern Hemispheres have opposite seasons. Consider our Earth, a beautiful blue marble pirouetting through the vastness of space. Seasons aren't about distance from the sun. It's Earth's tilt, about 23.5 degrees. This tilt causes seasonal changes. Northern Hemisphere tilts towards the sun for summer. Southern Hemisphere tilts away for winter. 6 months later, it reverses. This tilt drives our seasons. Tell me why some places get more lightning than others? Lightning. It's one of nature's most spectacular displays of raw power. But have you ever considered why some parts of our planet host these electrical extravaganzas far more frequently than others? The primary ingredients for a thunderstorm are warm, moist air near the surface and an unstable atmosphere. As this buoyant, humid air ascends, it cools, forming clouds. If the updrafts are strong enough, these clouds can grow to enormous heights, becoming towering cumulonimbus clouds. Regions near the Earth's equator receive the most direct and consistent sunlight, creating an environment ripe for thunderstorm genesis. Within these colossal thunderclouds, a fascinating electrical drama unfolds, leading to lightning. Consequently, areas like Central Africa, the Amazon basin, and parts of Southeast Asia experience some of the highest frequencies of lightning strikes on Earth. These regions are natural laboratories for studying atmospheric electricity. Tell me why wind chill makes it feel colder. Imagine stepping outside on a crisp, cold day. The thermometer reads 32 degrees Fahrenheit, or 0 Celsius. Now imagine another day with the same air temperature, but this time a biting wind is howling around you. You instinctively feel much colder, even though the thermometer insists the temperature hasn't changed. This isn't just a trick of your perception, it's a real phenomenon known as wind chill. Our bodies generate heat, creating a thin layer of warm air around our skin. When the wind picks up, it strips away that protective layer, increasing the rate at which your body loses heat. This process is a form of convective heat loss, making you feel colder. Meteorologists report a wind chill temperature to quantify how cold the air due to wind speed. Understanding wind chill is crucial for personal safety in cold climates. Tell me why the Sahara Desert used to be green. When we conjure an image of the Sahara, we picture vast sun-scorched dunes. Yet thousands of years ago, this now barren landscape was a vibrant green savanna. This period is known as the African humid period. The transformation was caused by long-term cyclical variations in Earth's orbital parameters, known as Milankovitch cycles. These orbital shifts altered the amount and distribution of solar radiation received by Earth. Around 11,000 to 5,000 years ago, the Northern Hemisphere experienced warmer summers. This strengthened the West African monsoon, bringing rains to the Sahara. The Green Sahara supported a rich ecosystem and human populations. As Earth's orbital parameters continued to change, the monsoon weakened and the desert reclaimed the land. The story of the Green Sahara is a testament to our planet's climatic sensitivity to subtle astronomical forcings. Tell me why rain sometimes evaporates before reaching the ground? Have you ever seen dark streaks trailing down from a cloud yet the ground remains dry? This is virga, rain that never reaches the ground. Precipitation forms and starts to fall. It meets dry air and evaporates. The entire water content can turn to vapor. Virga is common in arid regions. It creates wispy, tail-like streaks. Virga has meteorological significance. It can cause microbursts or downdrafts. Tell me why volcanoes can affect global weather. Volcanoes. These geological features can unleash unimaginable power. A large volcanic eruption can alter global weather patterns and climate for months or years. When a powerful volcano erupts, It injects a colossal plume of gases and particulate matter into the atmosphere. Among these gases, sulfur dioxide is a key player. Once in the stratosphere, SO2 forms tiny droplets of sulfuric acid, known as sulfate aerosols. These aerosols scatter incoming solar radiation, reflecting sunlight back into space, and causing a net cooling effect on the global climate. The 1815 eruption of Mount Tambora led to the year without a summer in 1816. The 1991 eruption of Mount Pinatubo caused a global average cooling of about 0.5 degrees Celsius. Volcanic impacts provide invaluable insights into climate sensitivity and the intricate feedback mechanisms within Earth's atmosphere. Tell me why the ozone layer is important for weather. The ozone layer is Earth's natural sunscreen, absorbing harmful ultraviolet radiation. However, it also influences atmospheric dynamics and weather patterns. The process of ozone formation and destruction releases heat, warming the stratosphere. This stratospheric warming creates a stable boundary, confining weather systems to the troposphere. The temperature gradients created by ozone absorption influence major atmospheric circulation patterns, including jet streams. Changes in stratospheric temperature and circulation can affect weather patterns at the surface. The Antarctic ozone hole has been linked to shifts in southern hemisphere weather patterns. The ozone layer is an active participant in generating global weather. Its influence on atmospheric dynamics underscores the interconnected nature of our planet's atmospheric layers. The ozone layer isn't just a passive shield. It's a silent conductor orchestrating atmospheric movements from high above. Tell me why tornadoes rarely happen in winter. Tornadoes are among nature's most ferocious displays, typically associated with spring and summer. But tornado warnings are rare during the cold heart of winter. The genesis of a tornado requires warm, moist air near the ground and atmospheric instability. This warm air provides the fuel for powerful updrafts that form supercell thunderstorms. Another crucial ingredient is wind shear, which helps initiate rotation. During winter months, these essential conditions are typically absent. The ground is cold and the air is drier, lacking the primary fuel source for severe thunderstorms. The atmosphere is generally more stable. While tornadoes can occasionally occur in winter, they are far less common and usually weaker. The cold, stable, and dry conditions of winter suppress the atmospheric dynamics necessary for tornadoes to form. Tell me why wind speeds are higher on mountains. Wind speeds tend to be higher at greater altitudes, and there's fascinating physics behind this. The primary reason is the diminishing effect of surface friction. Near the Earth's surface, wind encounters obstacles like trees and buildings, creating drag. As you ascend, the influence of surface friction lessens, allowing the air to move more freely. Mountains can also accelerate wind by funneling it through passes and valleys. This phenomenon is critical for activities like aviation and mountaineering. It influences the design of structures like wind turbines, often placed on elevated terrain. The next time you feel that bracing wind on a high peak, remember you're experiencing a fundamental principle of atmospheric fluid dynamics. Air liberated from the shackles of surface friction moves faster. This principle explains why winds howl louder on high. Tell me why wildfires create their own weather. Wildfires can generate and manipulate their own localized weather systems. The immense heat released by burning vegetation creates powerful updrafts. These updrafts form a convection column, drawing in cooler air and fanning the flames. In extreme cases, these updrafts can spawn fire whirls or firenadoes. If the convection column rises high enough, it can form pyrocumulus clouds. These clouds can produce localized rain and lightning, igniting new fires. The fire actively shapes its own microclimates, creating unpredictable fire behavior. Understanding these fire-atmosphere interactions is crucial for improving firefighter safety. It helps develop more effective strategies to combat intense wildfires. Wildfires are not just reacting to the prevailing weather, they're actively shaping it. We've explored the forces that shape our seasons, winds, and rains. From volcanoes to wildfires, nature's drama unfolds. Subtle changes can unleash incredible power. Each phenomenon tells a story of our dynamic planet. Understanding deepens our appreciation. Stay curious and hit subscribe for more mind-blowing facts. More mysteries await in the cosmos.